Let us start now with the central topic of differentiation. And the first thing we're going to look at are polynomial functions. A function with this shape is called a polynomial function of degree n, the degree being the exponent with the highest value. Fill in this example to show that you've got the value, the idea. Stop the film now, and here comes the result. The degree is the exponent with the highest value of x. So here we have x to the power of 5, so 5 is the degree. A5 is then the coefficient of the term x to the power of 5, so the number in front of it, so it's 3. Then A4 is the coefficient of the term with x to the power of 4. Well, there is none, so it is 0, and so on. For x squared, we have A2, it's minus 5. And here we have no x, so it's actually x to the 0. So this is A0, the constant term is 2. So this expression itself is called a polynomial. X is the variable. A0 is the constant term. An is the leading coefficient, the first one here, so it's the leading one, and it has to be non-zero. And ak is then the coefficient of the for the term with x to the power of k. So for example, a2 is the coefficient that stands in front of the x to the power of 2. For small n, these polynomials or functions have special names. So if n is 1, it is a linear function or polynomial. If n is 2, it's quadratic. If n is 3, it's cubic. And if n is 4, we call it quartic. We can write this expression here more short and more correct in summation notation. This means using the sigma. This here means just sum up for the terms ak times x to the power of k for k going from 0 to n. So ak for k being 0, we have a0 times x to the power of 0. X to the power of 0 is 1, so we get just a0. Then for k equals 1, we get a1 times x. This here, so we have a0, now a1x. For k being 2, we have a2 times x to the power of 2, and so on until in the end we are at an times x to the power of n, and we have to add them all up. So this is just a short notation for this here. The fundamental theorem of algebra now states that any polynomial p of x here can be written as a product of linear and non-factorizable quadratic polynomials. Let us look at an example. X to the power of 4 minus 1. Well, we can use the third binomial formula. We can write it as x squared minus 1 times x squared plus 1. So we have it already written as a product of quadratic polynomials. However, this is not yet complete because one of them is factorizable, namely the x squared minus 1. Applying again the third binomial formula, we get x plus 1 times x minus 1 times x squared plus 1. X squared plus 1 cannot be factorized, so the equation x squared plus 1 equals 0 has no solution. That's why we cannot factorize it. So we're done. We have factorized x to the power of 4 minus 1 to the maximum as product of linear polynomials and a quadratic polynomial. When factorizing a polynomial completely, we find its zeros. This means the values of x where p of x is 0. Let's look at an example. Let's find the zeros of this polynomial function x squared minus 2x minus 3. But first, let's factorize it. We can factorize it by using the Klammeransatz. So we have the two brackets. We know there must be an x and an x. The one is plus, one is minus. The product has to be 3. So there's only one possibility, 3 and 1. And then it has to sum up to minus 2. So it has to be x plus 1 times x minus 3. To find the zeros of the polynomial, we have to set p of x equal to 0, so we get x squared minus 2x minus 3 equals 0. Now using the factorization, we get the equation x plus 1 times x minus 3 equals 0, and this yields us x1 equals minus 1 and x2 equals 3. A small reminder regarding quadratic equations and expressions. To solve this equation, we could also use the midnight formula. Then we would find these two solutions, and then just using x minus x1, so we get x plus 1 times x minus x2, x minus 3, we have the factorization of this polynomial. Solve example 2 on your own, stop the film, and here comes the result. We have to set the expression equal to 0. Factorizing this, we use again two brackets, and we know that due to the 2x squared, it has to be 2x and x here, always assuming that there are some rational solutions, otherwise this will not work and we have to use the midnight formula. The product of the numbers in here has to be 15, and then we have to end up with 7x, so we have to look at potential candidates. It seems most obvious that 5 and 3 are good candidates. Well, 5 times 10, 2x will be 10x, and 3 times x is 3x, so the difference of the two is really 7x. So we need to insert here plus 5 and here minus 3, and we get here the second solution is minus 5, and here for the first solution, by setting 2x minus 3 equal to 0, we get 2x equals 3, so we get x1 is 3 halves. In example 3, we want to find the zeros of this polynomial here. We're additionally given that x minus 3 is a factor of this polynomial, so we can write this polynomial as x minus 3 times another polynomial. And to find this other polynomial, it means we have to divide our original polynomial here by x minus 3. And once we've done that, we can set p star of x equal to 0. What we'll get is a polynomial of degree 2, so we can solve that then simply. To solve this, we need to apply polynomial division. Try to do that on your own, stop the film, and here comes the result. We take the first term here on the left and divide it by the first term here on the right, so we get x to the power of 3 divided by x, so we get x squared. As the next step, we multiply this result with the divisor polynomial, so it's x minus 3, and subtract it from the original polynomial. So expand this expression, we get x to the power of 3 minus 3x squared. We write it exactly below the corresponding terms, and then we subtract the whole thing, so minus the whole thing. The x to the power of 3 cancels out, and here what remains is minus 3x squared. So what remains in total is minus 3x squared minus x plus 30, so we could copy the whole minus x plus 30 down here. But to simplify our life, we only copy the part that we need for the next step, which is the minus x. Now we take the remainder polynomial, which is now the minus 3x squared minus x plus the 30 here. And again, we take the term with the largest exponent, so minus 3x squared, and divide it here by the largest exponent of the divisor polynomial. And we get minus 3x. We take this result, minus 3x, and multiply it with x minus 3, and we expand it. And we get minus 3x squared plus 9x, and we subtract that. The x squared cancel out as it has to be, and here we get minus 10x. Let's take the plus 30 down from up there. Now we have to divide the minus 10x by the x here, and we get minus 10. We multiply the minus 10 by the x minus 3, expand it, we get minus 10x plus 30, we subtract that, and we get in the end 0, which means that the original polynomial here is really divisible by the x minus 3. This is the same as with integer division as we did in primary school. 15 divided by 3 is 5 with remainder 0, so 15 is divisible by 3.
16 divided by 3 is 5 with remainder 1, so 16 is not divisible by 3. So we can write the original polynomial as the product of x minus 3 times the result of the division. And now we can factorize the second bracket and we find this result here. Our task is to find the zeros of this polynomial here. So what we'll do is we set the polynomial equal to 0, inserting the expression for it, and now replacing it by this expression. We find now the results 3, 5, and minus 2 for the zeros. Obviously, normally you will, once you found this, write immediately down the zeros without doing this intermediate step. This is just for completeness here. Here on the bottom of the page, you find a description of the polynomial division algorithm that you can study by your own before we continue with the next example. To find out whether this polynomial here is a factor of this polynomial here, we have to perform a polynomial division and see if the remainder is 0 or not. Do that on your own, stop the film, and here comes the result. To perform the polynomial division, don't forget first to write the polynomials in descending order of the exponents of x. And second, it's really helpful here, there is no x squared in this expression, just insert a 0x squared. My experience is that students have problems if they don't do it. You don't actually need it. And we get in the end remainder x minus 2. Please note up here the 5x squared. Since I wrote here the 0x squared, we know where to put them, and then we have to subtract from what. Obviously, if it had nothing here, I have just to write it somewhere in between, and the result would still be the same. And we found that this 3x squared minus x plus 5 is not a factor of this polynomial. So our result is that the complete division yields x squared plus 2x minus 1 plus x minus 2, this here, divided by 3x squared minus x plus 5. That's the result of this division. Another way of looking at it, we can also say this here, the original polynomial, can be written as the product of the 3x squared minus x plus 5 times the x squared plus 2x minus 1, the result here, plus this remainder plus the x minus 2. In example 5, we have to find the factorization of this polynomial, and we're given two factors, x minus 1 and x plus 3. One way to solve it is just to divide this here by x minus 3, take the result and divide it then by x plus 3. We can, however, simplify our life by first taking the product of x minus 1 and x plus 3 and then divide this original polynomial by the product. This is then only one polynomial division and one multiplication, which is much less and simpler to do than two polynomial divisions. The idea is the same like here. When you have 10,000 divided by 8 divided by 125, you can rewrite it as 10,000 divided by 8 times 125. And well, then the whole thing becomes very simple. So go ahead, solve this on your own, and then here comes the solution. And so we find that the polynomial division yields 2x squared minus 11x plus 12. So the original polynomial can be factorized as x squared plus 2x minus 3 times 2x squared minus 11x plus 12. Now this we know can be factorized as x minus 1 times x plus 3, since that's the way that we got it. And the second bracket is factorized using two brackets, 2x and x, and we have twice minus, and then we see that using here 3 and 4, and we found the factorization. Now let us look at a very important corollary of the fundamental theorem of algebra. By corollary, we mean something that follows directly from the theorem. So we have a polynomial p of x, and now if p of c is 0, so some if for some value of xc, p of c is 0, then we know that the linear factor x minus c is a factor of the polynomial. The benefit of this corollary is that when we know a zero or some zeros of a polynomial, we can simplify the polynomial by using polynomial division and hence find probably also the rest of the zeros. Or if we're not given these zeros, but we can guess one, for example, if we have a polynomial of third degree and we can guess one of the zeros, then we can calculate the remaining two zeros using then the midnight formula maybe. How do we guess zeros? Well, we make a guess and typically we start with 1 or then with -1, and we check when we insert this value for x, so 1 or -1, we insert that into the polynomial p of x, whether it is really 0 or not. If it's not, we may take 2 and -2 and 3 and -3, and then slowly it is enough. So if it works with guessing, it should be with one of these numbers. Another idea is actually, or a help is, that if we have a polynomial where all coefficients are integers, ganze Zahlen, then we know that if there is a 0, if there is a value that with p of c equals 0, a value that is an integer, we know this is a divisor of the constant term. So we don't have to look for other potential guesses. So solve now example 6. This means first guess a 0, and then using that guess you can use polynomial division and find the remaining zeros. Stop the film, and here comes the solution. Let us start with the guess x equals 1. Let's insert 1 into p of x, and we get a number that is not equal to 0, so we know this guess is wrong. As a second guess, let's use x equals -1. Let's insert that again into the p of x, and we get that p of -1 is 0, so this guess is fine. X equals -1 is a 0. x1 equals -1. So now we have to divide the original polynomial by x minus x1, which means by x plus 1. And we find the result x squared plus x minus 12 with remainder 0 as it has to be. So we can write the polynomial now in factor form and factorize the second bracket as well. And we find x plus 1 times x plus 4 times x minus 3. And so we get the three solutions. x1 equals -1, and x2 equals -4, and x3 equals 3.